So let's talk a little bit about the Diels-Alder reaction and what's called the Endo rule and why we usually get the endo product. So if we take cyclopentadiene, which is a great diene because it's locked in the S-cis conformation, so it's very reactive. So this is our diene. And we treat this with some kind of dienophile. I'll choose a dialdehyde here. So we have two aldehydes at the end of our diene. So both of these have electron withdrawing groups. If I just draw one of them out, you know that they both have, an aldehyde has, of course, a carbonyl group. So this is going to pull electron density away from our dienophile, so making it even more reactive than it normally would be. So if we have a diene plus a dienophile, we know from class that we are going to end up with some kind of bicyclic product that will look something like this, where we have a double bond here, and this is the CH2 from our cyclopentadiene. If I just draw the arrows, the curved arrows for this mechanism, it would look something like this, where we have these coming over here, and then you have those electrons moving down there. So we ask ourselves, what is the major product of this reaction going to be? So we have these two aldehyde groups here. We have one here, and then we have one here. So where are these going to be on our bicyclic product that we have here? Well, if we take a look, now let me just draw this out a little bit larger. So if we take a look at the final product that we get from a reaction between cyclopentadiene, I should tie that bond up, we can either have our substituents pointing up or they can be pointing down. So when the substituents are pointing up, we call this the exo product. This is the exo product. And when the substituents are pointing down, this is called the endo product. The endo product. So endo products, endo products are syn to the larger bridge, okay? And exo products, so exo will be anti to larger bridge. Okay, and clearly you can see that this is the large bridge, and that this is the small bridge. So those are our two bridges. So you can see that the endo product is syn to the large bridge, and the exo product is anti to the large bridge. And the fact that we usually get, or we almost always observe the endo product. So we almost always observe the endo product when we do a Diels-Alder reaction. So the endo products are favored. And this is actually called the Endo rule. If you look in some textbooks, they actually call that the Endo rule. And the reason for that is because of the interaction between the p orbitals in our electron withdrawing group. So there's going to be p orbitals here, and the p orbitals in our pi bond. So there's some p orbitals here. We'll kind of draw them in. So there's an interaction that occurs between the p orbitals in our groups that are endo and our p orbitals in the diene that's formed. So due to that favorable interaction, this is why the endo product is preferred. And the endo, the reason they call it the endo is because it's kind of inside this pocket area that's formed. So we call this the endo, whereas the exo is outside of that pocket area that's formed of the larger of the two rings. So let me just erase that. So our desired product, what we're going to see is we should see exclusively or mostly the endo product. So we put our two aldehyde groups pointing downwards. And that would mean that our two protons are facing up. So the protons are exo, but our dienophile, the substituents on our dienophile are pointing down, and this is the endo product. And that is why we mainly see the endo product. And we call that the endo rule, and it's because of the favorable interaction between the p orbitals on our dienophile and the p orbitals on our diene. So it covers this in Klein's book a little bit, but I hope this clears up any confusion that you might have about the endo rule and Diels-Alder reactions.